Welcome to this next video in the playlist on vector spaces. Okay, so in this video what we're going to discuss is the basis of a dual vector space. And what we're going to see is that if you have a basis for the initial vector space, which you use to construct the dual vector space, then there's a very natural basis that you can pick for the dual vector space, which relates to the initial basis that you had on the initial vector space, and that's called the dual basis. Okay, so that's what we're going to see in this video. So to start off with then, let's just have a quick reminder of what a dual vector space is. Okay, so we start off with some vector space V, which is a vector space over some arbitrary field capital F here, and what we saw in the previous video in this playlist on vector spaces, which is entitled dual vector spaces, is that from this you can construct another vector space which is known as the dual vector space, and this dual vector space is notated V star, and it's also going to be a vector space that's over the field capital F here. Okay, now what are the elements of the dual vector space? Well, the elements of the dual vector space are going to be linear maps from the initial vector space to the field capital F. So just drawing a picture of this, let's let this box be the set of elements that are in the dual vector space. So this is going to represent our dual vector space V star here, and I'll just colour in this box in green here. And the actual elements within the dual vector space are quite strange, okay, and this is what takes a lot of getting used to when you first see this. They are functions, they're maps from the initial vector space V into the field capital F. Okay, so we might call one phi, like so, and phi will be a mapping from the vector space V into the field F. Okay, and this needs to be a linear map. After all, the field F, you can view that as being a vector space over the field F itself. So you need addition to obey a property, and you need scalar multiplication to obey a property. That it doesn't matter whether you firstly do the additional scalar multiplication prior to taking the image of that under this map, or if you first do the image taking and then you do the addition or the multiplication. Okay, so this needs to be a linear map. So all the elements in the dual vector space are linear maps from the vector space V to the field F. So to start off with then, to construct the dual vector space, what you do is you find absolutely every single linear map from the vector space capital V to the field F. You stick them all into this set here, and that's the set which you're going to use to construct the dual vector space. So then all you need to do after that is define an addition and a scalar multiplication law on this set, and then it's actually going to be a vector space. So let me just remind you of the addition and the scalar multiplication laws that we define on the dual vector space. So firstly, let's have addition. So if we've got two elements in our dual vector space, phi1 and phi2, which are both linear maps from the vector space V into the field F, then if we want to add them together, like so, the way that we define this is we define this new map, which is phi1 plus phi2, where this addition will be done in the dual vector space. This will be the map that takes any vector V from the vector space V over F here and takes it onto phi1 of V, and then you'll add it onto phi2 of V plus phi2 of V here, where this addition is done in the field rather than in the dual vector space. Okay, so I'll notate plus in the field by purple. So when we've got plus in the dual vector space, I'll notate that in green. Plus in pink here means addition in the field. Okay, so quite simply, if you want to know where this map phi1 plus phi2 is going to send any vector in your vector space capital V to, it's just going to be where does phi1 send this vector V, where does phi2 send this vector V, and add those two things together in the field. And that's going to be our new map, which we'll call phi1 plus phi2 here. And as I say, that addition sign needs to be coloured in green to remind us that it's addition in the dual vector space. So that's how we define addition in the dual vector space. And in the previous video on dual vector spaces, we went through this and, really examined it and made sure that it obeyed the axioms of a vector space addition law, i.e. those of an abelian group, and we made sure, for instance, that the actual answer here was always going to be another linear map and things like that. Okay, so we really did check this in the previous video. This is just a reminder. Okay, and scalar multiplication, if you've got some element of the field which you are scalar multiplying with an element of the dual vector space, so C scalar multiplied with this phi, which is an element of our dual space, this is going to be another map from the vector space V to the field F that's going to be in our dual space here, and it's going to map any vector V from the vector space capital V here, and it's going to take it onto, just by definition, C times phi of V, where this multiplication here is now done in the field rather than in the dual vector space. So again, if you want to know where this map C scalar multiplying phi actually is going to send any vector in the vector space, you just say, well, where did the original map phi send phi? Okay, that's phi of v here, and you just multiply that by this scalar c from the field, and you do that in the field because after all, phi of v is an element of the field, so you can quite easily multiply two elements of the field together. Okay, so that's how we define the addition and scalar multiplication laws on the dual vector space. And as I say, in the previous video we went through these and checked that they really do hold up, that they actually give a vector space structure on this set here. And that vector space structure that we've created now is what's called the dual vector space, or our original vector space V over F here. Okay, right, so now on to the meat of this video. We want to do the basis of a dual vector space. Now, to talk about bases, we need to be working with finite dimensional vector spaces. You can talk about bases in infinite dimensional vector spaces, but we haven't done any of that in this playlist. Okay, and really, to do it in any sort of interesting way, you really need analytic concepts to be able to do it. Okay, you can do it algebraically without analysis, but it's kind of lame if you don't have analysis, so it's more of a topic for analysis, infinite dimensional vector spaces. Okay, so we will take a finite dimensional vector space. So we're now going to assume that V is a finite dimensional vector space, which means that we can construct a nice finite basis for V. Okay, so V is finite dimensional, it's still a vector space over the field F, but now because it's finite dimensional, I can construct a basis. Okay, so let's say I construct my basis here, V1, V2, all the way up to Vn, where n is the dimension of the vector space of V. Okay, so here's some arbitrary basis, and we know how arbitrary bases are. We've seen this a lot in previous videos in this playlist. That you can select any set of vectors which spans the entire vector space and which is linearly independent, and that constitutes a basis. So there might be loads and loads of different bases, but we found one here. So here is our chosen basis. And remember, the incredibly important thing about a basis is because it spans the entire vector space and because it is linearly independent, you can take an arbitrary vector from your vector space, so an arbitrary little v from the vector space capital V, and you can write it as a linear combination of the basis vectors in a unique way. So you can write it as a linear combination of the basis vectors in one, that's the spanning, and only one, that's the linearly independent way. Okay, so V will equal A1 V1 plus A2 V2 plus all the way along to AN Vn, where these AI's are all from the field. Okay, so this is a linear combination of the basis vectors. We've put a scalar coefficient in front of all the basis vectors, okay, and then we've added them all together to create our vector V. And as I say, there is one and only one way to do that if this collection of vectors here is the basis. Okay, right, so we can express any vector in the vector space as a linear combination of the basis vectors. So the question now comes, we have this algebraic dual vector space, okay, which we've created from this vector space V. can we create a basis on our dual space? And is there a very natural basis to create on the dual space if we're using this basis for our original vector space V? And it turns out there is. There is a basis that it is very natural to now use for the dual vector space, which we'll call the dual basis, and I will notate this B star like so. As I say, you can obviously, there are loads of different bases most likely on your dual vector space, and you could use whichever one you like, but there is a very natural one to use given that you are using this one for your original vector space, okay, and this is going to be called the dual basis. Okay, and it's our job now to discuss what this dual basis is going to actually be. Okay, now before we actually do define what the dual basis is going to be for our dual vector space, what I'd like to do is explore with you a little bit more what a linear map in the dual vector space will actually do to any vector in our initial vector space. Okay? So remember, the elements in the dual vector space, these are all linear maps from our original vector space V onto the field F. Okay, so if we have one, so let's say we have phi, which is from our dual vector space here, and we're going to act, whoops, not V, we're going to act phi. I'll just try and repair that. So here's phi. We're going to take phi of this vector V, but we can take any vector in our vector space V and write it in terms of these basis vectors here. So we can write it as a linear combination, a1 v1 plus a2 v2 plus all the way along to an vn. Okay, so we're just exploring what will phi of a vector in our vector space actually be, where phi is some element of the dual vector space. Okay, and we can take any vector in our initial vector space and write it as a linear combination of the basis vectors for our initial finite dimensional vector space. Now, because this is a linear map, okay, we can work some magic on this because we've got lots of things added together. Now, because this is a linear map, we can split up those things that are added together, and then we've got things that are scalar multiplied together, and again we can pull out the scalar coefficients. So what this will become after we've finished with it is something of this form: a1 times phi of v1 plus a2 times phi of v2 plus all the way up to an times phi of vn. Now understand how incredible this is. We are using the linear map big time here because all of these additions and multiplications, they were in the initial vector space, which I'll colour in red here. Okay, so we've got scalar multiplications and additions in the initial vector space here. Now what have we turned all of this into? We've turned it into multiplications and additions in the field algebra. So this is now all field theory stuff here. However, the important message from this is that actually, if I know where the basis vectors are sent by this linear map phi in the dual vector space, then I know everything about this linear map. Okay, because any other vector in the vector space capital V can be written as a linear combination of those basis vectors, and then we know that linear maps respect linear combinations. Okay, so any other vector is just going to be mapped onto exactly this, where these scalar coefficients here are exactly the scalar coefficients that were in front of the basis vectors to give the correct linear combination for that vector in terms of those basis vectors. Okay, so as soon as you know where the basis vectors are sent, as soon as you know phi of v1, phi of v2, all the way up to phi of vn, as soon as you know those answers, what those are in the field, okay, they're all going to be elements of the field. Remember, phi maps vectors into the field. As soon as you know where they go, you know where every other vector goes, because of the fact that this is a linear map which therefore respects linear combinations. Okay, so that's very, very crucial, and that's going to be crucial for us to understand this dual basis. Okay, so let me now explain what the dual basis is going to be. So the dual basis, which we'll call B star, is going to be a very natural basis for us to have on our dual vector space. Now remember, a basis is just elements from the vector space. So this basis of the dual vector space is going to just be elements of the dual vector space, i.e. it's going to be maps from the original vector space V into the field F. Okay, now I'm going to call these vectors, or covectors I should call them, from the dual vector space names, and then I'll actually tell you what they're going to be. So the first thing to say is that you're going to have the same number of them as you have in the basis of the original vector space here. Okay, so in fact it's going to be the same dimension as the original vector space, so we'll have v1 star, v2 star, all the way up to vn star. So the star denotes that we're talking about the dual vector space now. Okay, now how am I going to define these? Well, these are going to be the covectors which are defined by the fact that they will map the basis vectors onto very special elements of the field. Okay, so let's start with v1 star. It's best to do it with a specific example. v1 star will map v1 onto the multiplicative identity in your field. Okay, so v1 star will map v1 onto the multiplicative identity in the field, which will denote 1. Okay, meanwhile it will map everything else, all the other basis vectors, v2, v3, v4, all the way up to vn, it will map them onto the additive identity in your field. It will map them onto 0. Okay, so remember I've just shown you that any linear map from the vector space capital V to the field is completely and utterly described by where it sends the basis vectors. So all the information you need to specify a linear map is where do the basis vectors go. I am now completely specifying this linear map v1 star by telling you where the basis vectors go. It will send the basis vector v1 onto the multiplicative identity in your field, and it will send all the other basis vectors, so v2, v3, all the way down to vn. It will send all of those onto the additive identity in your field. Okay, now, what does that overall mean that v1 star acting on any vector v in your initial vector space capital V over f would actually do? Well, of course, we'll decompose our vector into its linear combination in terms of the basis vectors. So we'll get v1 star acting on a1 v1 plus a2 v2 plus all the way along to an vn. Okay, then we'll apply the fact that we can break this down into its linear, into this form here, because this is a linear map. Okay, so it will we want it to be a linear map, so we want it to be the case that it can be broken down into this. So it'll just be a1 v1 star of v1 plus a2 v1 star v2 plus all the way along to an v1 star vn, like so. Okay, I'll just move this up a little bit. Whoops. Right, so now what we can say then is we know the answers to where it sends the basis vectors. We know that it will send all of the other basis vectors onto 0 in the field. Now 0 multiplied by anything in the field will give 0 back again. So that means all of these portions just go, they all vanish, they become the additive identity. v1 star of v1 here is the multiplicative identity 1, so this just becomes equal to a1. So it just maps any vector in the vector space onto what this coefficient in front of the first basis vector was, and this of course is some element of the field capital F. Okay, so that's how these basis vectors are going to be defined. Now of course that's just v1 star, but you can probably guess what we're going to do with the rest. v2 star will do a very similar thing, but it will now move on to the second basis vector, so we'll then send the second basis vector onto 1 and all the others onto 0. v3 star will send v3 onto 1 and all the others onto 0. All the way up to vn star will send vn onto 1 and all the others onto 0. Okay, and these then are going to be our dual basis vectors for this dual vector space. Okay, and as I say, more generally, what will they do to any vector? So if I've got vi star here, okay, so where I can vary from 1 to n now, it will send any vector just onto the coefficient that was in front of that ith basis vector. So it will just send it onto ai, which is an element of the field. Okay, so I hope you understand that that's the coefficient in front of the ith basis vector, which we were using to describe this vector in terms of its coordinates with respect to. Okay, so it will just send it onto its ith coordinate if we use that terminology. Okay, right, so that's how we're going to define these dual basis vectors. Okay, now I think we'll have a break here whilst that just settles in, and in the next video what we'll do is have a look at how we can then take an arbitrary element of the dual vector space and write it as a linear combination of these basis vectors in the dual basis of the dual vector space. And then what we'll do is actually do an example of taking a dual vector space and constructing the dual basis.